Tonight the journey begins with one of the biggest questions in all of astronomy. How many galaxies exist in the universe? For centuries humanity believed the Milky Way was everything. Then powerful telescopes revealed countless islands of stars scattered across the darkness of space. But the deeper scientists look, the larger the universe appears, and the harder it becomes to count what lies beyond. Before settling in, please take a moment to like this video and subscribe to the channel. It helps us continue creating calm, fascinating journeys through space and time. Now, as the stars slowly emerge from the darkness, the story of the universe's unimaginable scale begins. The observable universe exists as a bounded region defined by the reach of light and the expansion of space. It represents the portion of the universe from which light has had time to arrive since the earliest moments after cosmic origins. Beyond this region, space may continue without a sharp physical edge, but information from those regions has not yet reached any observer. The boundary is not a solid wall, but a horizon shaped by time, distance, and the finite speed of light. Within this framework, distance is not measured only by physical separation, but by how long light takes to travel through expanding space. As the universe expands, space itself stretches, and the path of light becomes longer over time. This means that regions once visible can move beyond observational reach if expansion carries them away faster than light can traverse the increasing distance. The observable universe is therefore dynamic, changing slowly as cosmic expansion progresses. The outermost visible layer of this region is defined by the cosmic microwave background, a faint glow present in every direction. This radiation is a remnant from a time when the universe first became transparent to light. At earlier stages, the universe was filled with a dense plasma of charged particles that scattered photons continuously. As expansion cooled the universe, atoms formed, and light began to travel freely. That moment marks the transition into an observable cosmos. The light from that early era has travelled for billions of years before reaching present space. It arrives today as extremely stretched wavelengths shifted into the microwave portion of the electromagnetic spectrum. This background radiation forms a spherical shell around all observers, giving a map of the universe at a very early stage. It represents the farthest direct observation possible using light alone. Inside this horizon, space is filled with structures at different stages of development. Galaxies are distributed unevenly, forming clusters, sheets, and vast empty regions. These patterns reflect the influence of gravity, acting over immense timescales. Even though galaxies appear fixed in position on human timescales, they are all moving, carried by the expansion of space and by local gravitational interactions. The scale of the observable universe is often described in terms of distance light has travelled since the earliest epoch. Because expansion stretches space, the current distance to the farthest observable regions is greater than the age of the universe multiplied by the speed of light. This creates a universe that is larger than the simple product of time and light speed would suggest in a static space. At the centre of observation is every location in the universe simultaneously. The observable horizon is not centred on a single point in an absolute sense. Instead, each observer, regardless of position, experiences their own surrounding sphere of observable space. This means that the observable universe is a shared concept but locally centered everywhere. The structure of this region is shaped by early fluctuations in density that grew over time. Slight variations in the distribution of matter allowed gravity to pull material together, forming the first seeds of cosmic structure. These seeds expanded into large formations that define the modern cosmic landscape. As space expands, the boundary of observability slowly increases for some regions, allowing newly emitted light from distant structures to reach observers. However, at the same time, other regions pass beyond reach, disappearing from future observation. This balance creates a horizon that evolves gradually rather than remaining fixed. The concept of a cosmic horizon also relates to limits imposed by the speed of light. No signal can travel faster than light in a vacuum, and this rule establishes a fundamental constraint on how information moves through the universe. Because of this constraint, the observable region is always finite, even if the universe itself may be much larger or possibly infinite. Within this finite region, matter and energy are distributed according to the history of cosmic expansion and cooling. Early uniformity gave way to structure formation, leading to the complex arrangement of galaxies seen today. Despite this complexity, the large-scale structure remains statistically uniform when viewed across sufficient distances. The observable universe therefore represents both a physical limit and a temporal window. It is limited in space by distance and in time by the age of the earliest visible light. Everything within it is seen not as it is now, but as it was when the light began its journey across expanding space. A deeper description of this boundary relies on different ways of measuring distance in an expanding universe. Astronomers use the concept of redshift, which describes how light stretches to longer wavelengths as space expands during its journey. The greater the redshift, the farther back in time the light originated. This allows the observable universe to be mapped not only in distance, but also in look-back time, meaning the duration light has travelled before reaching present space. Another way of describing cosmic distance is through comoving coordinates. In this framework, positions are measured as if the expansion of space were factored out, allowing the large-scale structure of the universe to be described in a more stable reference system. Comoving distance helps illustrate how galaxies remain part of a larger expanding pattern, even as the space between them increases over time. Look-back time provides a temporal perspective on the observable horizon. When observing distant galaxies, the light seen today represents conditions that existed billions of years ago. The farther the object, the earlier in cosmic history it is observed. This creates a layered view of the universe where different distances correspond to different epochs of development, all contained within the same observable region. The combination of these measurement methods reveals that the observable universe is not simply a static sphere but a structured volume shaped by time-dependent processes. Its boundary is defined simultaneously by how far light has travelled and how the expansion of space has altered that path. These combined effects create a horizon that is both geometric and temporal in nature. Within this framework, every direction in space leads to a similar limit, producing a uniform observational boundary around all points. This uniformity arises from the large-scale homogeneity of the universe, where matter is evenly distributed when viewed at the largest scales. Even though local regions contain complex structures such as galaxies and clusters, the overall pattern remains consistent across the observable region. The early universe transparency emerges as a gradual transition from an opaque, hot, dense state into a cosmos that allows light to travel freely across space. In the earliest moments after cosmic expansion begins, the universe exists as an extremely energetic plasma, a state of matter where electrons and atomic nuclei do not remain bound together. In this environment, photons constantly interact with charged particles scattering in all directions. Light cannot travel in straight paths, and the universe remains visually opaque even though it is filled with radiation. As expansion continues, the universe cools steadily. Temperature decreases because the energy of radiation is spread across an increasing volume of space. This cooling changes the behavior of matter at the smallest scales. Electrons begin to slow enough that they can be captured by atomic nuclei. When this happens, neutral atoms form for the first time. This transition is known as recombination, not because it is a repeated process, but because electrons and nuclei combine into stable structures after a long period of separation. Before this transition, the universe is dominated by a dense mixture of hydrogen, nuclei helium, nuclei electrons and photons. Photons interact frequently with free electrons through scattering, and this continuous interaction prevents light from moving in straight, uninterrupted lines. The universe at this stage behaves like a thick fog where visibility is limited to very short distances. Any photon released into this environment is quickly redirected, losing information about its origin. As recombination begins, conditions shift across the entire observable universe in a relatively short span of cosmic time. The formation of neutral atoms reduces the number of free charged particles available to scatter light. With fewer interactions occurring, photons begin to travel longer distances without interruption. This marks the beginning of transparency. The universe does not become transparent in a single instant everywhere, but the transition occurs rapidly on cosmological timescales, creating a distinct boundary in time rather than space. The surface associated with this transition is known as the last scattering surface. It is not a physical boundary in the conventional sense, but a region in time and space from which the oldest freely traveling photons originate. These photons form the cosmic microwave background observed today. When these photons last interacted with matter, the universe was significantly smaller, denser, and hotter than it is at present. As space expanded, their wavelengths stretched, shifting them into the microwave portion of the electromagnetic spectrum. This radiation now fills the universe uniformly, arriving from all directions. It provides a snapshot of the universe at the moment it became transparent. The temperature of this radiation is nearly uniform, with only tiny fluctuations that reflect small differences in density at that time. These fluctuations later become the seeds of cosmic structure, guiding the formation of galaxies and larger systems. Following recombination, the universe enters a period often described as the cosmic dark age. During this time, no stars have yet formed, and the universe contains primarily neutral hydrogen and helium gas. Without luminous sources, space becomes filled with matter that does not emit visible light. Although the universe is now transparent, it remains dark, because there are no internal sources of illumination. Light exists, but it is primarily the fading radiation from earlier epochs. During this dark age, gravity begins to play an increasingly important role in shaping matter. Slight variations in density cause gas to slowly gather into regions of higher concentration. These regions begin to collapse under their own gravity, setting the stage for the formation of the first stars. Even though this process takes place over long periods, it originates from the small fluctuations present at the time of recombination. The transparency of the universe allows these gravitational processes to proceed without constant interference from radiation pressure. In the earlier opaque phase, interactions between photons and matter helped maintain a tightly coupled system. Once photons decouple from matter, radiation no longer dominates the dynamics of structure formation. Matter becomes free to evolve under gravity alone, leading to increasing complexity in distribution. The cosmic microwave background remains as the most direct evidence of this transition. It is observed today as a nearly uniform background radiation, with a temperature just a few degrees above absolute zero. This faint glow represents the cooled remnant of the intense radiation that filled the early universe. Its uniformity confirms that the early universe was highly homogeneous, while its small variations reveal the initial conditions that shaped everything that followed. As photons travel through expanding space, their wavelengths continue to stretch. This redshifting process reduces their energy over time. What was once visible or even high-energy radiation becomes microwave radiation after billions of years of expansion. This transformation is not due to changes in the photons themselves, but due to the expansion of the space they travel through. The moment of transparency also defines a limit to direct observational knowledge. Any information from earlier than recombination is carried only indirectly through subtle imprints on the cosmic microwave background. There is no direct light that reaches observers from before this period because earlier photons cannot travel freely. They remain trapped in the dense plasma of the early universe. Within the transparent universe that follows, matter distribution becomes increasingly structured. Gas clouds form, merge and evolve, influenced by both gravity and residual thermal motion. Over time, these processes lead to the first ignition of nuclear fusion in dense regions, marking the end of the cosmic dark age and the beginning of stellar activity. The transition from opacity to transparency therefore represents a fundamental turning point in cosmic history. It separates a universe dominated by radiation and frequent interactions from one governed primarily by gravity and large-scale structure formation. This change allows light to carry information across vast distances, enabling the observable universe to develop its layered structure of time and space. Even though transparency is established early, its effects continue to shape observations across all later cosmic epochs. The cosmic microwave background remains embedded in every direction of the sky, acting as a persistent record of the moment when the universe first became visible in a physical sense. It serves as both a boundary and a reference point for understanding all subsequent cosmic evolution. The early transparent universe is not static but continues to expand and cool. As space grows, matter becomes more diffuse in some regions and more concentrated in others. These evolving conditions set the stage for the complex network of galaxies that will later emerge, all originating from the simple, nearly uniform conditions present at the moment of recombination. The primordial structure seeds exist as extremely small variations in the density of matter in the early universe, forming the earliest recognizable patterns from which all later cosmic structure develops. After the universe becomes transparent, matter is no longer tightly coupled to radiation, and these tiny differences in density begin to grow under the influence of gravity. At this stage, the universe appears nearly uniform on large scales, but careful measurements reveal that it is not perfectly smooth. Instead, it contains faint regions of slightly higher density and slightly lower density distributed throughout space. These variations are not large enough to create immediate structures such as stars or galaxies. Instead, they represent subtle imprints left by processes occurring in the very early universe, possibly during a phase of rapid expansion known as cosmic inflation. Inflation describes a period when space itself expanded extremely quickly, stretching quantum fluctuations to cosmic scales. These fluctuations, originally occurring at microscopic levels, become magnified into density variations across vast regions of space. Although the exact details of inflation remain uncertain, observations of the cosmic microwave background strongly support the existence of such primordial fluctuations. Once matter decouples from radiation during recombination, these fluctuations become gravitationally active. Regions with slightly higher density contain more matter and therefore exert a slightly stronger gravitational pull on surrounding material. Over long periods of time, this difference causes matter to slowly accumulate in these regions. At the same time, regions with slightly lower density contain less gravitational attraction and gradually become more diffuse as matter flows toward denser areas. This process does not occur quickly, but it operates continuously across billions of years. The growth of these primordial seeds follows a hierarchical pattern. Small-scale structures begin forming first, gradually merging into larger and more complex systems. In the earlier stages, the universe contains mostly neutral hydrogen and helium gas distributed almost evenly, with only minor variations. As gravity amplifies these variations, gas begins to collect into clumps. These clumps represent the first steps toward the formation of stars and galaxies, Although they are not yet luminous or fully organized, dark matter plays a central role in shaping these early structures. Dark matter is a form of matter that does not interact with light, making it invisible to direct observation. Its presence is inferred through its gravitational effects on visible matter. In the early universe, dark matter begins to collapse into structures even before ordinary matter fully responds, because it does not interact with radiation. This allows dark matter to form gravitational wells regions where ordinary matter later accumulates. These wells act as the scaffolding for all subsequent galaxy formation. As baronic matter, meaning ordinary matter composed of protons and neutrons, falls into these dark matter structures, it begins to heat up due to compression. This heating does not immediately lead to star formation, but it increases pressure within collapsing regions. Over time, as gas continues to accumulate, conditions become suitable for the ignition of nuclear fusion, marking the birth of the first stars. However, this stage occurs later in cosmic history and remains beyond the immediate scope of primordial structure seeds. The distribution of these seeds is not random in a chaotic sense, but follows statistical patterns that can be measured across the sky. Observations of the cosmic microwave background reveal tiny temperature differences corresponding to regions of slightly different density in the early universe. These variations are extremely small, often only a few parts in 100,000, yet they contain the full information needed to explain the large-scale structure of the universe observed today. This remarkable connection between early fluctuations and present-day galaxies demonstrates how sensitive cosmic evolution is to initial conditions. As time progresses, the influence of gravity becomes increasingly dominant over other forces on large scales. While pressure from gas resists collapse on small scales, gravity continues to pull matter into denser regions. This balance between collapse and resistance determines the size and shape of the first structures. Some regions collapse quickly, forming compact clumps, while others take longer to evolve, creating a diverse range of early cosmic environments. The growth of structure is also influenced by the expansion of the universe. As space expands, it stretches the distances between regions, slowing down the collapse of large-scale structures. However, within regions where gravity is strong enough, local collapse continues despite expansion. This interplay between expansion and gravity leads to a complex evolution in which some structures form early, while others remain diffuse for longer periods. Over time, the initially small density variations evolve into a network of interconnected structures. These structures begin to form filament sheets and nodes, creating the early framework of what will later be known as the cosmic web. Even though this web becomes more pronounced in later epochs, its origins lie in the primordial seeds established shortly after recombination. The cosmic microwave background continues to provide the most detailed map of these early fluctuations. By studying variations in temperature and polarization across the sky, scientists can reconstruct the statistical properties of the primordial universe. These measurements show that the fluctuations are nearly scale invariant, meaning they have similar strength across a wide range of scales. This property supports theoretical models of the early universe and provides constraints on the physics of inflation and cosmic expansion. The primordial structure seeds also determine the distribution of galaxies across vast distances. Regions that began with slightly higher density tend to evolve into galaxy clusters, while regions with lower density become cosmic voids areas with relatively few galaxies. This large-scale pattern reflects the initial conditions encoded in the early universe and preserved through billions of years of cosmic evolution. Although the universe at this stage remains mostly uniform in appearance, the seeds of complexity are already embedded within it. The difference between a region that will later become a massive galaxy cluster and one that will remain relatively empty is determined by these tiny initial variations. Over time, gravity amplifies these differences, transforming subtle fluctuations into the large-scale structures observed in the modern universe. The study of primordial structure seeds therefore provides a direct link between the earliest moments of cosmic history and the present-day arrangement of galaxies. It reveals that the universe's large-scale structure is not random, but emerges from well-defined physical processes acting on small initial variations. These processes operate across immense timescales, gradually transforming simplicity into complexity without abrupt transitions or discontinuities. In this early stage of structure formation, the universe remains dark, vast, and mostly featureless to direct observation. Yet beneath this simplicity lies a detailed framework that will eventually shape every galaxy star system and planetary environment. The primordial seeds represent the beginning of this long transformation, marking the point where small differences in density begin to define the architecture of the cosmos. The dark matter framework emerges as an invisible structural component of the universe that shapes the formation and evolution of all visible matter through gravity alone. It does not emit, absorb, or reflect light, making it undetectable through direct observation. Its presence is inferred entirely from its gravitational influence on galaxies, galaxy clusters, and the large-scale motion of matter. In the early universe, long before galaxies fully formed, dark matter already begins organizing itself into vast diffuse structures that define the underlying architecture of cosmic space. Unlike ordinary matter, dark matter does not interact with electromagnetic radiation. This means it does not experience pressure from light and does not scatter photons. As a result, it evolves differently from baryonic matter, which is composed of protons, neutrons, and electrons. While ordinary matter remains coupled to radiation in the early universe and responds to heating and cooling, dark matter moves almost exclusively under the influence of gravity. This difference allows dark matter to begin collapsing into dense regions earlier than visible matter can follow. These early dark matter structures form what can be described as gravitational wells. A gravitational well is a region where matter is pulled inward by the concentration of mass, creating a natural attraction point for surrounding material. In the early universe, these wells appear as subtle but growing variations in the distribution of dark matter. Over time, they deepen as more dark matter accumulates, creating a complex network of interconnected structures. Baryonic matter begins to respond to these wells once it decouples from radiation after recombination. Before this moment, the pressure from photons prevents ordinary matter from collapsing easily. After decoupling, gas becomes free to move under gravity and starts falling into the pre-existing dark matter structures. This process marks a critical shift in cosmic evolution, as visible matter begins to trace the invisible scaffolding already established by dark matter. The interaction between dark matter and baryonic matter does not involve direct contact or collision. Instead, it occurs through the shared influence of gravity. As gas falls into dark matter wells, it compresses and heats up. This heating is caused by gravitational potential energy converting into thermal energy as particles move inward. Although this process increases temperature, it is not yet sufficient to ignite nuclear fusion in most regions during the earlier stages. Dark matter structures vary in scale from small halos surrounding future galaxies to enormous filaments stretching across hundreds of millions of light years. These filaments connect dense regions, forming a web-like pattern that defines the overall distribution of matter in the universe. Between these filaments lie vast empty regions known as voids, where the density of both dark and visible matter is significantly lower. The formation of this cosmic framework is gradual. Small dark matter halos form first, merging over time into larger structures through gravitational attraction. This hierarchical growth leads to increasingly complex systems. Smaller halos merge into larger halos, which then become the cores of galaxy groups and clusters. This process continues over billions of years, shaping the universe into a structured network rather than a random distribution of matter. Numerical simulations play a crucial role in understanding the dark matter framework. By modeling the gravitational interactions of large numbers of particles representing dark matter, scientists can reproduce the large-scale structure of the universe observed today. These simulations show that even small initial fluctuations in dark matter density naturally evolve into filamentary networks similar to those seen in galaxy surveys. This agreement between simulation and observation strongly supports the existence of dark matter, even though it has not been directly detected. Observational evidence for dark matter comes from several independent sources. The rotation curves of galaxies show that stars in the outer regions move faster than expected based on visible mass alone. This indicates the presence of additional unseen mass extending beyond the visible boundaries of galaxies. Similarly, the motion of galaxies within clusters suggests that much more mass is present than can be accounted for by luminous matter. Gravitational lensing, the bending of light around massive objects, provides further evidence by revealing mass distributions that do not correspond to visible structures. In the early universe, the influence of dark matter is particularly important for structure formation. Because it begins collapsing earlier than baryonic matter, it establishes the initial conditions for where galaxies will eventually form. Without dark matter, baryonic matter alone would not have had enough time to form large-scale structures within the age of the universe. The presence of dark matter accelerates the formation of gravitational wells, allowing galaxies to emerge earlier and more efficiently. As baryonic matter accumulates within dark matter halos, it begins to cool through radiation processes. Cooling allows gas to lose energy and settle into more compact regions, increasing density further. Over time, these dense regions become the sites where the first stars ignite. Although star formation belongs to a later stage in cosmic evolution, it is directly dependent on the underlying dark matter framework. The cosmic web formed by dark matter filaments remains stable over long periods of time. Even as galaxies form and evolve within it, the large-scale structure of dark matter changes slowly. Galaxies move along filaments, often merging at intersections where density is highest. These intersections become galaxy clusters, some of the most massive structures in the universe. Dark matter does not appear uniform on small scales. Instead, it forms clumps of varying density. These clumps influence the shape and evolution of galaxies by providing gravitational centers around which visible matter organizes. The distribution of these clumps determines how galaxies rotate, how they merge, and how they interact with their surroundings. Despite its invisibility, dark matter plays a defining role in shaping the observable universe. Every galaxy cluster and filament exists within its framework. Without it, the large-scale structure of the universe would be fundamentally different, likely lacking the complexity and richness observed today. The dark matter framework therefore represents an unseen but essential layer of cosmic structure. It operates continuously, silently shaping the universe through gravity alone, providing the foundation upon which all visible matter organizes itself into stars, galaxies, and eventually the large-scale cosmic patterns that define the universe as a whole. The first galaxy formation epoch begins when dense regions of gas guided by underlying dark matter structures collapse enough for gravity to overcome internal pressure. In the early universe, matter is still relatively uniform on large scales, but within dark matter, halo's baryonic gas slowly gathers into increasingly compact regions. As these regions grow denser, their internal pressure rises, yet gravity continues to draw material inward. This balance gradually shifts. until conditions become suitable for the first gravitationally bound luminous systems. At this stage, the universe contains mostly hydrogen and helium, the simplest and most abundant elements formed during earlier cosmic nucleosynthesis. These gases fill space in vast clouds stretching across regions defined by dark matter filaments. As gas falls into these filaments and collects in halo centers, it begins to fragment into smaller clumps. Each clump represents a potential site of future star formation, but not all clumps evolve at the same rate. Some collapse quickly, while others remain diffuse for longer periods. The first galaxies do not form as fully structured spiral or elliptical systems. Instead, they appear as irregular, compact assemblies of gas and early stars. These early galaxies are often small compared to modern galaxies, yet they play a crucial role in shaping the evolution of the universe. Their formation marks the beginning of sustained light production, on a large scale ending the long period where the universe was mostly dark except for the cosmic microwave background. As gas continues to collapse, density increases at the centers of these proto-galaxies. When density and temperature reach sufficient levels, nuclear fusion begins in the cores of the first stars. This process releases energy in the form of light and heat, transforming gravitational energy into radiation. The ignition of these first stars changes the surrounding environment, heating nearby gas and influencing further star formation. The radiation from early stars does not remain confined to individual galaxies. It interacts with surrounding gas, ionizing neutral hydrogen in a process known as reionization. During reionization, high-energy photons from young stars and early galaxies strip electrons from hydrogen atoms, returning much of the universe's gas to an ionized state. This process occurs gradually across different regions, creating a patchwork of ionized and neutral zones that evolve over time. The structure of early galaxies is strongly influenced by their environment within the cosmic web. Galaxies that form in dense regions tend to grow faster, merging with nearby structures and accumulating more mass. In contrast, galaxies forming in less dense regions remain smaller and evolve more slowly. This variation leads to a wide diversity in galaxy size, shape, and composition even in the early universe. Star formation within these early galaxies is highly active. Gas clouds collapse rapidly, producing massive short-lived stars that emit intense radiation. These stars live much shorter lives than many later generation stars, quickly exhausting their nuclear fuel and ending in energetic explosions. These events distribute heavier elements into surrounding space, enriching the interstellar medium and changing the chemical composition of future generations of stars. As galaxies grow, they begin to interact more frequently. Gravitational attraction causes smaller galaxies to merge into larger ones. These mergers reshape galactic structure, often triggering bursts of star formation due to the compression of gas during collisions. Over time, repeated mergers lead to the formation of larger, more stable galaxies with organized structures such as disks and bulges. Dark matter continues to play a central role throughout this epoch. Each galaxy is embedded within a dark matter halo that extends far beyond the visible boundaries of stars and gas. These halos provide the gravitational framework that holds galaxies together. Even as galaxies merge and evolve, their dark matter halos combine and restructure, maintaining the underlying cosmic architecture. The earliest galaxies also serve as sources of chemical evolution in the universe. Initially composed almost entirely of hydrogen and helium, these systems begin producing heavier elements through stellar processes. When massive stars reach the end of their life cycles, they release these elements into space where they become part of new gas clouds. Over time, this cycle enriches the universe with elements necessary for the formation of planets and complex structures. Observations of distant galaxies allow scientists to study this epoch directly. Because light from these galaxies takes billions of years to reach present space, they are seen as they were in the early universe. These observations reveal that early galaxies are smaller, more irregular, and more actively forming stars compared to many modern galaxies. They also provide insight into how quickly galaxies formed after the universe became transparent. The distribution of galaxies during this epoch is not random. It reflects the underlying pattern of dark matter filaments and density fluctuations established earlier. Galaxies form preferentially along these filaments, creating a network-like structure that becomes more pronounced over time. This structure gradually evolves into the cosmic web seen in the modern universe. As the first galaxy formation epoch progresses, the universe transitions from a relatively simple state dominated by gas and dark matter into a complex system filled with luminous structures. The appearance of galaxies marks a turning point in cosmic evolution, where light from stars begins to dominate the observable universe, replacing the faint afterglow of the cosmic microwave background as the primary source of information about cosmic structure. This epoch lays the foundation for all subsequent cosmic development. Larger galaxies, galaxy clusters, and more complex structures all originate from the processes initiated during this period. The interaction between gravity gas dynamics and star formation establishes patterns that continue to shape the universe over billions of years. Even though galaxies appear as distinct objects in the sky, they are part of a larger interconnected system. Their formation is governed by shared physical processes operating across vast distances and timescales. The first galaxy formation epoch therefore represents not only the birth of individual galaxies, but also the emergence of the large-scale structure that defines the universe as a whole. The cosmic web development describes the emergence of a vast interconnected structure that fills the universe on the largest observable scales. This structure is not made of solid material, but of patterns in the distribution of galaxies' gas and dark matter. It forms a network of long filaments, dense nodes, and empty voids, shaped entirely by gravity acting over billions of years. The cosmic web is not visible as a physical object, but it becomes apparent when mapping the positions of galaxies across space. As the universe evolves beyond the first galaxy formation, epoch individual galaxies begin to cluster together along the same underlying dark matter framework. These clusters are not randomly placed but follow preferred paths, defined by earlier density fluctuations. Matter flows along these paths, gradually accumulating in regions where filaments intersect. These intersections become the most massive structures in the universe, known as galaxy clusters. Between these dense regions lie vast voids. Voids are enormous spaces with relatively few galaxies and very low matter density. They are not completely empty, but compared to surrounding filaments, they contain far less visible structure. The presence of voids highlights the uneven distribution of matter that develops over cosmic time. While gravity pulls matter into dense regions, surrounding areas become increasingly depleted, reinforcing the contrast between structure and emptiness. The formation of the cosmic web is driven primarily by dark matter. Because dark matter dominates gravitational interactions on large scales, it shapes the overall architecture of the universe. Ordinary matter follows this structure, falling into the gravitational wells created by dark matter filaments and halos. Over time, this process enhances the contrast between dense and empty regions, making the web-like pattern more pronounced. Gas within these filaments moves slowly under gravitational influence. As it flows toward denser regions, it becomes compressed and heated. In some areas, this gas cools efficiently and forms stars within galaxies. In other regions, especially within filaments, connecting galaxy clusters, gas remains diffuse and forms extended bridges of matter. These bridges can stretch across millions of light years, connecting massive structures in a continuous network. The cosmic web evolves through continuous accretion and merging. Smaller structures are drawn toward larger ones, gradually increasing the mass of galaxy clusters at filament intersections. This process is hierarchical, meaning that small structures form first and later combine into larger ones. Over time, this leads to increasingly complex arrangements of matter, with clusters embedded within superclusters, connected by long filamentary chains. Computer simulations of cosmic evolution reproduce the formation of this web-like structure with remarkable consistency. By modeling dark matter as a large number of interacting particles under gravity, these simulations show how initial tiny fluctuations naturally evolve into filament networks. The agreement between these simulations and observational data from galaxy surveys supports the idea that the cosmic web arises from fundamental gravitational processes acting on early density variations. The visible universe traces this underlying structure. Galaxies are not evenly distributed in space, but are found along the filaments of the cosmic web. When mapped on large scales, these galaxies form patterns resembling a three-dimensional network. This network extends across hundreds of millions of light-years, revealing the large-scale order underlying what might otherwise appear as a random distribution of objects. As the cosmic web develops, the contrast between dense filaments and empty voids becomes more extreme. Matter continues to flow from low-density regions into high-density structures, deepening voids and strengthening filaments. This redistribution of matter is a slow but continuous process that shapes the universe over billions of years. Galaxy clusters at the intersections of filaments grow increasingly massive through repeated mergers. These clusters contain hundreds or even thousands of galaxies bound together by gravity. Within them, galaxies interact frequently, sometimes merging to form larger systems. The environment within these clusters is dynamic, with high-energy processes influencing the evolution of galaxies and surrounding gas. The cosmic web also influences the motion of galaxies. Rather than moving randomly, galaxies tend to follow the direction of filaments, guided by gravitational attraction toward denser regions. This motion contributes to the gradual assembly of large-scale structures, reinforcing the web-like pattern across cosmic time. Although the cosmic web is defined by dark matter and gravity, its presence is revealed through luminous matter. Galaxies act as tracers of the underlying structure, allowing astronomers to map the invisible framework of the universe. By observing the distribution of galaxies across different distances, the shape of the cosmic web can be reconstructed in 3 dimensions. Over time, the cosmic web becomes more defined as matter continues to accumulate in existing structures. Filaments grow thicker, clusters become more massive, and voids expand. This ongoing evolution reflects the long-term influence of gravity, acting on initial conditions established in the early universe. The cosmic web development represents a transition from relatively simple early structures into a highly interconnected cosmic system. It provides the large-scale framework within which all galaxies evolve. Every galaxy, including those similar to the Milky Way, exists within this network, influenced by its position within filaments, nodes, or voids. Even though the cosmic web spans immense distances, its origin lies in extremely small fluctuations, present shortly after the universe became transparent. These tiny variations, amplified over time by gravity, eventually produced the vast and complex structure observed today. The cosmic web therefore connects the earliest moments of cosmic history to the present-day arrangement of galaxies across the universe. Galaxy growth through mergers describes the process by which galaxies increase in size and complexity, by colliding and combining with one another over cosmic time. After the first galaxies form within dark matter halos, they do not remain isolated systems. Instead, they move through space along filaments of the cosmic web, gradually influenced by gravity from nearby structures. When galaxies come close enough, their mutual gravitational attraction begins to alter their shapes and trajectories, eventually leading to mergers. A galaxy merger is not an instantaneous event, but a long process that unfolds over hundreds of millions to billions of years. As two galaxies approach each other, their outer regions begin to interact first. These outer regions contain diffuse gas stars and extended dark matter halos. Gravitational forces distort these structures, pulling material into elongated shapes known as tidal features. These features can extend far beyond the main bodies of the galaxies, creating streams of stars and gas that stretch across space. During the early stages of interaction, the galaxies may pass near each other multiple times. Each passage transfers energy and angular momentum between the systems, gradually altering their orbits. This repeated interaction can lead to stronger gravitational binding, eventually causing the galaxies to lose orbital energy and move closer together. Over time, they settle into a shared gravitational system, beginning the process of full merging. As the merger progresses, gas clouds within the galaxies are compressed by gravitational forces. This compression increases density and temperature in localized regions, triggering bursts of star formation. These bursts, often called star formation episodes, produce large numbers of new stars in relatively short periods of cosmic time. The rate of star formation during mergers can be significantly higher than in isolated galaxies, making these events important drivers of stellar population growth. The central regions of merging galaxies become increasingly active as gas flows inward. This inward movement is caused by gravitational torques that remove angular momentum from gas clouds, allowing them to spiral toward the center. In many cases, this leads to the formation of dense central structures where stars form rapidly. If sufficient gas is present, these central regions can become extremely luminous and compact. Dark matter halos surrounding the galaxies also merge during this process. As the halos combine, they form a larger gravitational structure that eventually stabilizes after the merger completes. The resulting system is typically more massive and extended than either of the original galaxies. This growth through hierarchical merging is a fundamental mechanism by which large galaxies, including those similar to the Milky Way, assemble their mass over time. Not all mergers are equal in scale. Some involve galaxies of similar size known as major mergers, while others involve a large galaxy absorbing a much smaller companion known as minor mergers. Major mergers often result in dramatic changes in structure, sometimes transforming spiral galaxies into more elliptical shapes. Minor mergers tend to have more subtle effects, gradually increasing mass and altering outer structures without completely reshaping the galaxy. The gravitational interaction during mergers can also disturb existing stellar orbits. Stars which rarely collide directly due to vast distances between them are instead redistributed into new orbital patterns. This redistribution can create extended halos of stars surrounding the merged galaxy. These halos contain remnants of earlier structures, preserving evidence of past interactions. Gas behavior during mergers is more complex than stellar dynamics, because gas can collide, compress, and radiate energy. As gas clouds collide, they lose kinetic energy through radiation, allowing them to settle into denser configurations. This process enhances central star formation and contributes to the build-up of galactic cores. In some cases, large amounts of gas are funneled into the central region, fueling extremely energetic processes. Mergers can also influence the activity of central supermassive black holes. As gas accumulates in the central region, some of it may fall into the black hole, releasing vast amounts of energy in the process. This activity can produce luminous emissions that outshine the rest of the galaxy for a period of time. Although the detailed physics of black hole accretion belongs to smaller scales, Its triggering is closely connected to the large-scale dynamics of galaxy mergers. Over long periods, repeated mergers contribute to the hierarchical growth of structure in the universe. Small galaxies form first, then merge to create larger systems, which continue to merge into even larger galaxies and clusters. This process reflects the underlying structure of the cosmic web, where matter flows along filaments toward dense nodes. The outcome of a merger depends on multiple factors, including the mass ratio of the galaxies, the amount of gas present, and the geometry of their encounter. Some mergers produce smooth, stable galaxies with well-defined structures, while others result in irregular systems with chaotic distributions of stars and gas. Over time, gravitational relaxation tends to smooth out these irregularities, leading to more stable configurations. Observations of distant galaxies provide direct evidence of mergers occurring throughout cosmic history. Many galaxies observed at earlier times appear distorted or irregular, consistent with ongoing interactions. In the present universe, merger remnants can still be identified by their structural features such as extended tidal streams and unusual stellar distributions. Galaxy growth through mergers is therefore a central mechanism in cosmic evolution. It transforms small, irregular early galaxies into larger, more complex systems. It redistributes matter across scales, fuels star formation, and shapes the structure of galaxies within the cosmic web. Through this continuous process of interaction and combination, galaxies evolve from simple initial structures into the diverse population observed in the universe today. Deep-field observations provide a method for studying extremely distant and faint galaxies by focusing telescopes on small regions of seemingly empty sky for long periods of time. These observations reveal that even areas of the sky that appear dark at first glance contain vast numbers of galaxies when viewed with sufficient sensitivity. Each point of light represents a galaxy seen as it existed billions of years in the past, due to the finite speed of light and the expansion of space. The principle behind deep-field imaging is based on prolonged exposure. By collecting light over extended durations, telescopes can detect photons that are too faint to be observed in shorter exposures. As more light accumulates, increasingly distant and dim objects become visible. This technique does not change the universe itself, but improves the ability to observe its most distant regions. The result is a layered view of cosmic history, where different depths correspond to different epochs of galaxy formation and evolution. Early deep-field observations conducted with space telescopes reveal a universe densely populated with galaxies at many different stages of development. Some appear as small, irregular structures, while others show more defined shapes, such as spirals or elongated forms. Many of these galaxies are observed as they were in the early universe shortly after their formation. Their light has travelled for billions of years before reaching present detectors, providing a direct look into cosmic history. These observations show that galaxy formation was already well underway in the early universe. Contrary to earlier expectations that galaxies would form slowly over long periods, deep-field images reveal that many galaxies appeared relatively soon, after the universe became transparent. This indicates that the processes governing structure formation were efficient, allowing matter to collapse and form luminous systems within a relatively short cosmic time frame. Deep-field surveys also reveal that galaxies are distributed unevenly across space. Even in very distant regions, galaxies are not randomly scattered, but tend to cluster together along large-scale structures. This clustering reflects the influence of dark matter and the cosmic web which guide the formation and distribution of galaxies. The patterns observed in deep fields are consistent with the idea that galaxies form within a pre-existing framework shaped by gravity. As observational technology improves, deeper and more detailed surveys become possible. Infrared observations are particularly important for studying very distant galaxies. Because the expansion of the universe stretches light toward longer wavelengths, light from early galaxies is often shifted beyond visible wavelengths. Infrared instruments can detect this stretched light, allowing astronomers to observe galaxies that would otherwise remain hidden. These advanced observations reveal even earlier stages of galaxy formation. Some galaxies appear extremely small and faint, indicating that they are among the first generations of cosmic structures. These objects often contain intense regions of star formation, producing large amounts of light despite their small size. Their presence helps trace the timeline of galaxy assembly and provides insight into the earliest phases of structure growth. Deep field data also helps refine estimates of galaxy abundance. By counting the number of galaxies observed in small regions of sky and extrapolating statistically, astronomers can estimate how many galaxies exist across the observable universe. This method relies on the assumption that the small region observed is representative of the larger cosmos. While there are uncertainties in this assumption, repeated observations in different directions support its validity. The results of deep field surveys suggest that the universe contains an extremely large number of galaxies, far more than can be individually catalogued. These estimates have evolved over time as observational techniques improve, especially with the introduction of more sensitive instruments. Each improvement reveals additional faint galaxies that were previously undetectable, increasing the estimated total count. Deep field observations also provide information about the evolution of galaxies over time. By comparing galaxies at different distances, it becomes possible to reconstruct how galaxies change in size, shape, and composition. Distant galaxies tend to appear smaller and more irregular, while closer galaxies often show more developed structures. This pattern reflects the ongoing process of galaxy growth and evolution throughout cosmic history. The combination of deep field imaging and cosmological models creates a coherent picture of the universe's structure. Observations confirm that galaxies are not uniformly distributed but follow the large-scale patterns predicted by simulations of dark matter evolution. This agreement between observation and theory strengthens the understanding of how cosmic structures form and evolve. Even though deep field observations cover only small regions of the sky, they provide a statistically significant window into the broader universe. The extreme depth of these images allows astronomers to observe galaxies at different stages of development, simultaneously effectively compressing cosmic time into a single view. This provides a powerful tool for studying how the universe changes over billions of years. As observational limits continue to improve, deeper surveys reveal increasingly faint and distant galaxies. Each new generation of telescopes extends the observable boundary further back in time, approaching the earliest moments of galaxy formation. These observations continue to refine estimates of galaxy abundance and improve understanding of the universe's structure. Deep field observations therefore serve as one of the primary methods for studying the total number of galaxies in the universe. By revealing vast numbers of faint and distant systems, they provide the empirical foundation for statistical estimates of cosmic abundance. These measurements form a critical link between theoretical models of structure formation and the observable distribution of galaxies across space and time. Galaxy counting methods rely on a combination of direct observation, statistical sampling, and theoretical modeling to estimate the total number of galaxies in the observable universe. Because it is impossible to observe every galaxy individually, astronomers use carefully selected regions of the sky as representative samples. These regions are studied in detail, and the number of galaxies within them is measured under different observational depths and wavelengths. The results are then scaled to the full sky, taking into account variations in galaxy density across different directions. At the core of these methods is the concept of completeness. Completeness refers to how many galaxies are detected compared to how many actually exist within a given observational limit. No telescope can detect every galaxy, especially the faintest and most distant ones. Some galaxies are too dim, too small, or too far away for current instruments to observe directly. To account for this, astronomers model the population of undetected galaxies based on the properties of those that are observed. One of the key tools in galaxy counting is the luminosity function. This function describes how many galaxies exist at different brightness levels. Brighter galaxies are easier to detect, while fainter ones require deeper observations. By understanding the distribution of brightness, astronomers can estimate how many faint galaxies are missing from observations. This allows them to correct raw counts and produce more accurate estimates of total galaxy numbers. Deep surveys across different regions of the sky are combined to reduce bias. Since the universe is not perfectly uniform on small scales, some regions contain clusters of galaxies, while others contain fewer objects. By averaging across many different areas, astronomers obtain a more reliable statistical picture. This approach assumes that large-scale uniformity holds meaning that the universe is homogeneous when viewed at sufficiently large scales. Distance also plays a central role in galaxy counting. As distance increases, galaxies appear fainter and more redshifted due to the expansion of the universe. Redshift shifts light toward longer wavelengths, making distant galaxies more difficult to detect in visible light. To address this, observations are conducted across multiple wavelength bands, including infrared, which can detect highly redshifted light from early galaxies. Selection effects must be carefully considered. These effects arise when observational limits influence which galaxies are detected. For example, a survey may detect many bright galaxies, but miss a large population of faint ones. Without correction, this would lead to underestimation of total galaxy numbers. Astronomers apply correction models based on known detection limits and instrument sensitivity to account for these missing populations. Another important method involves extrapolation from observed volume. By measuring the number of galaxies within a known volume of space, astronomers can estimate the average density of galaxies. This density can then be applied to the entire observable universe, adjusted for variations in structure such as clusters and voids. This method assumes that the sampled volume is representative of the larger cosmos when averaged over large enough scales. Simulations of cosmic structure also support galaxy counting methods. By modeling the evolution of dark matter and baryonic matter from early conditions, simulations can predict how many galaxies should exist at different epochs. These predictions are compared with observational data to refine models and improve accuracy. When simulations and observations align, confidence in galaxy estimates increases. Gravitational lensing provides an additional indirect method for detecting otherwise unseen galaxies. Massive objects such as galaxy clusters can bend light from more distant galaxies, magnifying their brightness. This effect allows astronomers to observe galaxies that would otherwise be too faint to detect. Lensing observations help fill in gaps in galaxy counts, particularly at extreme distances. Another challenge in galaxy counting is distinguishing between galaxies and other astronomical objects. At very high distances, compact galaxies may appear similar to bright star clusters or unresolved light sources. Advanced image processing and spectral analysis are used to classify objects accurately. Spectral data helps confirm whether an object is a galaxy by identifying characteristic emission or absorption patterns. As observational technology improves, the estimated number of galaxies continues to be refined. Earlier surveys suggested lower totals due to limited sensitivity, while more recent deep-field observations have revealed additional faint populations. Each improvement in telescope capability extends the observable range and increases the completeness of galaxy catalogues. The structure of the universe also influences galaxy counts. Because galaxies are distributed along the cosmic web, some regions contain higher concentrations of galaxies than others. Statistical methods account for this clustering by analyzing multiple independent regions and averaging results. This reduces the impact of local overdensities or underdensities on global estimates. Galaxy counting methods also consider the evolution of galaxies over time. Distant galaxies represent earlier stages of development, often smaller and more irregular. These differences in appearance can affect detection rates, as younger galaxies may be harder to identify or classify. Models of galaxy evolution help correct for these effects, ensuring that early-stage galaxies are properly included in estimates. Through the combination of direct observation, statistical modeling, and theoretical simulation, astronomers construct a comprehensive framework for estimating galaxy abundance. While no single method provides a complete answer, the convergence of multiple approaches produces consistent results. These results suggest that the observable universe contains an extremely large number of galaxies, far exceeding early expectations based on limited observational data. Galaxy counting methods therefore represent a synthesis of observational astronomy and cosmological theory. They translate limited snapshots of the universe into a broader statistical understanding of cosmic structure. Through careful correction, modeling and comparison, these methods provide the foundation for estimating how many galaxies exist within the observable universe. The Hubble Deep Survey results mark a turning point in the effort to measure how many galaxies exist in the observable universe by extending direct observation to unprecedented faintness and distance. Early space-based observations reveal that even small, seemingly empty patches of sky contain thousands of galaxies when viewed with sufficient exposure time. Each galaxy appears as a faint smudge or compact structure representing light that has traveled for billions of years through expanding space before reaching detectors. The Hubble Space Telescope enables these observations by operating above Earth's atmosphere, avoiding atmospheric distortion and absorption that limit ground-based telescopes. With long exposure imaging, the telescope accumulates extremely faint photons over many hours or even days. This allows the detection of galaxies that are far beyond the reach of earlier surveys. These deep images show that the universe is far more populated than previously understood, especially at great distances. The Hubble Deep Field observations focus on a very small region of the sky that initially appears almost empty. However, when observed with extreme sensitivity, this region reveals a dense population of distant galaxies. These galaxies are seen at different stages of development, from relatively mature systems to small irregular structures that existed in the early universe. The diversity within such a small field suggests that galaxy formation is widespread and occurred across nearly all regions of space. As exposure techniques improve, even deeper observations become possible. The Hubble Ultra Deep Field extends this approach by collecting light over even longer periods, revealing galaxies that existed only a few 100 million years after the beginning of the transparent universe. These galaxies are extremely faint and often appear as small compact objects with irregular shapes. Their detection confirms that galaxy formation began relatively early in cosmic history. The results of these deep surveys provide key data for estimating total galaxy numbers. By counting galaxies in a small field of view and scaling the results across the entire sky, astronomers can estimate the number of galaxies in the observable universe. However, this process requires careful correction for observational limits, since even the deepest Hubble images cannot detect the faintest or most distant galaxies. One of the major findings from these surveys is that galaxy counts increase significantly when observing deeper into space. As sensitivity improves, more faint galaxies become visible, suggesting that earlier surveys underestimated the true population. This implies that the universe contains a large number of low-luminosity galaxies that contribute significantly to total counts, but are difficult to detect individually. Hubble observations also reveal the evolution of galaxy structure over time. Distant galaxies seen as they existed in the early universe often appear smaller, clumpier, and less organized than nearby galaxies. This reflects the ongoing process of galaxy growth, where small irregular systems gradually merge and evolve into larger, more structured forms over billions of years. The distribution of galaxies in deep fields also confirms large-scale uniformity when averaged across sufficient distances. Although small-scale clustering is evident, the overall density of galaxies remains consistent in different directions of the sky. This supports the cosmological principle which states that the universe is broadly uniform when viewed on very large scales. Gravitational lensing effects are occasionally visible in deep-field images where massive foreground objects distort and magnify the light from distant galaxies. These lensing events allow astronomers to detect even more distant and faint galaxies than would otherwise be possible. Such observations extend the effective reach of deep surveys and improve estimates of galaxy abundance. The Hubble data also provides constraints on the rate of galaxy formation in the early universe. The presence of numerous galaxies at high redshifts indicates that structure formation occurred efficiently soon after recombination and the end of the cosmic dark age. This suggests that the underlying dark matter framework provided strong gravitational guidance for early galaxy assembly. As data from multiple deep field surveys are combined, a more complete picture of galaxy distribution emerges. These datasets show that galaxies exist in vast numbers across all observed directions, with no significant large-scale voids in the overall distribution of luminous matter. This uniformity strengthens statistical models used to estimate total galaxy counts. The improvement from early Hubble observations to later deep surveys highlights the importance of observational depth in cosmology. Each increase in sensitivity reveals new populations of galaxies, especially faint dwarf systems that dominate in number but not in brightness. These faint galaxies play a crucial role in the overall structure of the universe, even though they are difficult to observe individually. Hubble Deep Field results also serve as a benchmark for newer telescopes. Future instruments build upon these findings by extending observations into infrared wavelengths and achieving even greater sensitivity. This allows astronomers to observe galaxies at earlier times and refine estimates of total galaxy abundance further. Overall, the Hubble Deep Survey results demonstrate that the universe contains an enormous number of galaxies distributed across space and time. These observations provide direct evidence that galaxy formation is widespread and efficient, supporting models that predict a highly populated cosmos shaped by dark matter and cosmic expansion. James Webb refinements represent a significant advancement in the measurement of distant galaxies by extending observational reach deeper into infrared wavelengths. This extension is essential because light from the earliest galaxies is stretched by cosmic expansion, shifting it beyond visible light into infrared regions of the spectrum. By detecting this shifted light with greater sensitivity, newer instruments reveal populations of galaxies that were previously too faint or too distant to observe. The improved resolution and sensitivity of infrared observations allow astronomers to see galaxies that formed only a few 100 million years after the universe became transparent. These galaxies are not only distant but also represent some of the earliest stages of galactic development. Many appear small and compact, often with irregular shapes and intense regions of star formation. Their brightness is influenced by rapid stellar activity, where young massive stars emit large amounts of radiation over short timescales. These observations refine earlier estimates of galaxy abundance by revealing additional populations of faint galaxies that were not detected in earlier surveys. As more sensitive instruments probe deeper into space, the number of observable galaxies increases, suggesting that the universe contains a larger total population than previously calculated. This does not change the physical universe itself, but improves the completeness of observational data. One of the key contributions of infrared observations is the ability to trace galaxy formation across different epochs with greater clarity. By observing galaxies at various redshifts, it becomes possible to reconstruct how galaxies evolve from small irregular systems into larger, more structured forms. This evolutionary sequence shows that galaxy formation is continuous rather than abrupt, with gradual changes occurring over billions of years. The distribution of early galaxies observed in infrared surveys remains consistent with the large-scale structure defined by dark matter. Even at extreme distances, galaxies are not randomly scattered, but tend to align along filaments and cluster in dense regions. This reinforces the idea that the cosmic web was already influencing matter distribution at very early times, guiding the formation of the first luminous structures. Infrared observations also help resolve uncertainties in galaxy counting methods by improving detection of low luminosity systems. Many galaxies emit relatively little visible light, especially in their early stages. These faint systems are easier to detect in infrared because their light is less affected by scattering and absorption. As a result, infrared surveys increase the completeness of galaxy catalogues and reduce underestimation in total counts. The refinement of galaxy counts through these observations also highlights the importance of distinguishing between intrinsic brightness and observational limits. Some galaxies appear faint not because they are small or inactive, but because their light has travelled across vast cosmic distances and has been significantly redshifted. Correcting for these effects is essential for accurate population estimates. As infrared data accumulates, it becomes possible to better model the early stages of galaxy assembly. Observations indicate that galaxy formation begins earlier than previously assumed, with structures forming soon after the first dark matter. Halos become sufficiently dense. These early systems grow through accretion of gas and mergers, gradually building more complex galaxies over time. The improved clarity provided by infrared observations also helps identify previously unresolved structures within distant galaxies. Regions that once appeared as single objects are now seen to contain multiple components, including star-forming clumps and interacting substructures. This reveals that early galaxies are more dynamically active than earlier observations suggested. By combining infrared data with visible light surveys, astronomers construct a more complete picture of galaxy distribution across cosmic time. This multi-wavelength approach allows for cross-verification of galaxy counts and reduces uncertainties caused by observational bias. It also improves understanding of how different types of galaxies contribute to overall population estimates. The James Webb observations confirm that the universe contains a vast number of faint distant galaxies that significantly contribute to total galaxy counts. These galaxies are often smaller and less luminous than nearby systems, but are far more numerous. Their detection helps bridge the gap between theoretical predictions and observational data. Infrared refinements also improve understanding of how star formation rates evolve over time. Early galaxies often show intense periods of star formation, which gradually decrease as galaxies grow and stabilize. This trend affects galaxy brightness and influences how many galaxies can be detected at different distances. The increasing depth of observational data continues to reveal that galaxy formation is both widespread and efficient. Even in the early universe, conditions allow for rapid assembly of structures within dark matter halos. This efficiency supports models that predict a highly populated universe, where galaxy formation begins early and continues across cosmic time. James Webb refinements therefore represent a crucial step in reducing uncertainty in galaxy counts. By extending observational reach and improving sensitivity, they reveal a more complete and detailed view of the universe's structure. This leads to more accurate estimates of how many galaxies exist within the observable cosmos and strengthens the overall understanding of cosmic evolution. The unobservable universe limits define the regions of space that lie beyond the reach of any signal that can ever be received, even in principle, due to the expansion of space and the finite speed of light. These limits are not physical edges or barriers, but are instead determined by the structure of space-time itself. They arise because certain regions are moving away faster than light can bridge the growing distance, making their information permanently inaccessible to any observer. Within the observable universe, light from distant galaxies has had enough time to travel through expanding space and reach current detectors. Beyond this region, however, there exist areas where light emitted today or in the future will never arrive. This creates a distinction between what is observable and what is fundamentally unobservable, even if those regions contain galaxies or large-scale structures similar to those within view. The boundary between observable and unobservable space is shaped by cosmic expansion. As the universe expands, distant regions of space recede from each other. In some cases, this recession is slow enough that light can still travel across the increasing distance. In other cases, expansion outpaces the ability of light to close the gap, causing regions to become causally disconnected. Over time, more regions may cross this threshold, gradually leaving the observable domain. This limit is closely related to the concept of the cosmic event horizon. The event horizon in cosmology defines the maximum distance from which signals emitted now can ever reach an observer in the future. Unlike the particle horizon, which defines the current observable boundary based on past light, the event horizon is concerned with future communication possibilities. Together, these horizons describe the full causal structure of the universe. Inside the observable region, galaxies can be studied through their emitted light, allowing reconstruction of their properties and history. Beyond the event horizon, however, galaxies may exist but remain permanently hidden. Their light, even if emitted over vast periods, will never arrive due to accelerating expansion driven by dark energy. This acceleration increases the separation between distant regions, reinforcing the limits of observation. Dark energy plays a central role in shaping these limits. It is a form of energy that appears to be uniformly distributed throughout space and contributes to the accelerated expansion of the universe. As space expands faster over time, more distant galaxies cross the threshold beyond which they can no longer be observed. This means that the observable universe is not only finite, but also gradually shrinking in terms of what future observations can access. The unobservable universe is not empty by definition. It may contain structures similar to those within the observable region, including galaxies, clusters, and cosmic web structures. However, because no information from these regions can reach observers, their properties must remain unknown. The existence of these regions is inferred from cosmological models that assume large-scale uniformity beyond the observable boundary. Cosmic inflation, a rapid expansion phase in the very early universe, also contributes to the concept of unobservable regions. If inflation occurred over a sufficiently large scale, it could have produced regions of space that are causally disconnected from each other even at the earliest times. These regions would evolve independently, each with its own observable universe separated by distances too vast to bridge through light signals. Within this framework, the observable universe is understood as one region within a potentially much larger or even infinite cosmic expanse. The unobservable portion may contain structures similar in nature, but inaccessible in practice or principle. This distinction is essential for interpreting galaxy counts, since all estimates are limited to the observable region only. The limits of observation also influence how galaxy abundance is interpreted. All measured galaxy counts apply strictly to the observable universe. If the universe extends beyond this boundary in a similar way, then the total number of galaxies in existence could be vastly larger than observed estimates. However, because no direct information can be obtained from beyond the horizon, this remains a theoretical extension rather than an observational result. As cosmic expansion continues, the boundary of what is observable evolves. Some distant galaxies remain visible for long periods, slowly fading as their light becomes increasingly redshifted and diluted. Others eventually disappear from view entirely as their emitted light fails to overcome the expansion of space. This dynamic nature of the horizon means that the observable universe is not static but changes over time. The distinction between observable and unobservable space is therefore fundamental to cosmology. It defines the limits of empirical knowledge and separates regions that can be studied from those that cannot. All galaxy counting methods, deep field observations, and infrared surveys operate entirely within this boundary, meaning that their results describe only a portion of the full universe. Even though the unobservable universe cannot be directly measured, its existence is consistent with the same physical laws that govern the observable region. Gravity expansion and matter distribution are assumed to operate uniformly on large scales, suggesting that similar structures likely exist beyond observational reach. However, this remains an extrapolation based on symmetry and theoretical modelling rather than direct evidence. The unobservable limits therefore frame the context in which all galaxy estimates are understood. They establish the maximum boundary of empirical astronomy, while also highlighting the possibility that the universe may extend far beyond what can ever be seen or measured. Within this boundary, all known galaxies exist, but beyond it the cosmic landscape remains inaccessible and inferred only through theory. Estimated galaxy totals arise from combining observational surveys, statistical extrapolation, and cosmological modelling into a single coherent range of values, describing how many galaxies exist within the observable universe. These estimates do not represent a direct count, since individual identification of every galaxy is impossible due to limitations in sensitivity, distance, and cosmic redshift. Instead, they represent a carefully constructed synthesis of partial observations extended across the full sky. The process begins with deep observational fields that sample extremely small regions of space in great detail. Within these narrow windows, astronomers identify galaxies at a wide range of distances and brightness levels. These samples provide a baseline density of galaxies per unit area of sky and per unit volume of space. However, because each field covers only a tiny fraction of the sky, statistical scaling is required to infer total numbers. This scaling assumes that the observed region is representative of the universe as a whole when averaged over sufficiently large scales. While local variations exist due to clustering and voids, the large-scale distribution of matter is considered statistically uniform. This assumption allows astronomers to extend measured densities to the entire observable sky, producing initial estimates of galaxy abundance. Early estimates based on visible light surveys suggested a relatively modest number of galaxies. However, as observational depth increased, especially through space-based telescopes, it became clear that many faint and distant galaxies were not being detected. These low-luminosity systems are far more numerous than bright galaxies and contribute significantly to total counts, even though they are individually difficult to observe. Infrared observations further expanded these estimates by revealing galaxies whose light has been stretched beyond visible wavelengths. Many early galaxies emit primarily an ultraviolet and visible light, which is shifted into the infrared region due to cosmic expansion. Without accounting for this shift, a large portion of the galaxy population would remain undetected, leading to underestimation of total numbers. Cosmological simulations also play a central role in estimating galaxy totals. These simulations model the evolution of dark matter and baryonic matter, from early density fluctuations through to the formation of galaxies and large-scale structures. By comparing simulated galaxy populations with observed distributions, scientists can refine their estimates of how many galaxies should exist at different epochs and brightness levels. One of the key insights from these combined approaches is that the universe contains a very large population of small faint galaxies. These systems are often overlooked in earlier surveys because they emit less light and are harder to distinguish from background noise. However, they are thought to dominate galaxy counts numerically, even though larger galaxies dominate in mass and brightness. Gravitational lensing provides additional constraints on galaxy abundance. When massive objects bend and magnify light from distant background galaxies, they reveal objects that would otherwise remain invisible. These lensing events help correct for observational bias by uncovering galaxies that fall below normal detection thresholds. They also confirm that faint galaxies exist in large numbers at extreme distances. As more advanced telescopes extend observational reach, estimates of galaxy totals have been revised upward. Each improvement in sensitivity reveals additional populations of faint galaxies, especially at high redshifts. These revisions demonstrate that earlier counts were limited primarily by technological capability rather than actual absence of galaxies. Despite these improvements, uncertainty remains in the exact total number of galaxies. This uncertainty arises from several factors, including incomplete detection of faint objects, variations in galaxy luminosity functions, and assumptions about uniformity across unobserved regions. While models reduce these uncertainties, they cannot eliminate them entirely. Current estimates suggest that the observable universe contains hundreds of billions to potentially over 1 trillion galaxies, depending on the inclusion of the faintest and smallest systems. This range reflects the limits of current observational technology and modeling precision. It also reflects the continuous refinement of data as new instruments improve detection capabilities. The estimated totals are not static values but evolving results. As surveys become deeper and more sensitive, the number of detected galaxies increases, leading to updated statistical models. This dynamic process ensures that galaxy counts remain aligned with the best available evidence while accommodating new discoveries. Another important factor in galaxy estimation is the role of cosmic evolution. Galaxies change over time, merging, growing and evolving in brightness. This means that galaxies observed at different distances represent different stages of development. Accounting for this evolution is essential when translating observations into total population estimates. The relationship between observed galaxies and total galaxies depends heavily on detection limits. Even the most powerful telescopes cannot observe the faintest or most distant systems directly. As a result, a significant portion of the galaxy population must be inferred rather than observed. This inference is grounded in physical models of galaxy formation and evolution. Despite uncertainties, multiple independent methods converge on similar ranges for galaxy abundance. This convergence increases confidence in the estimates, even though exact numbers remain uncertain. The agreement between deep field observations, infrared surveys, gravitational lensing and simulations suggests that the overall picture of a highly populated universe is robust. Estimated galaxy totals therefore represent one of the most important statistical results in cosmology. They summarize the combined outcome of observational astronomy and theoretical modeling, providing a numerical description of the universe's large-scale structure. These estimates continue to evolve as new data becomes available, gradually refining the understanding of how many galaxies exist within the observable cosmos. Uncertainty in cosmic counts arises from the limits of observation, the complexity of galaxy formation, and the dependence on models that extend beyond directly measurable data. Even though modern surveys provide extremely detailed maps of the universe, they cannot capture every galaxy, especially the faintest and most distant ones. This creates a natural margin of uncertainty in all estimates of total galaxy numbers. One major source of uncertainty comes from detection limits. Telescopes can only observe galaxies above a certain brightness threshold. Objects below this threshold remain invisible even if they are abundant. Because the universe contains many low-luminosity galaxies, especially in its early stages, a significant portion of the population must be inferred indirectly. This inference relies on models of how galaxy brightness is distributed, but these models themselves carry assumptions that introduce variation in results. Another source of uncertainty is cosmic variance, the statistical variation in galaxy distribution across different regions of space. Although the universe is statistically uniform on very large scales, smaller observed regions can differ significantly in density. One deep field may contain more galaxies than another, simply due to natural clustering patterns. When scaling from limited samples to the full sky, these variations introduce uncertainty into global estimates. The luminosity function used to describe the distribution of galaxy brightness is also not perfectly known at all distances. While it is well measured for nearby galaxies, it becomes increasingly uncertain for very distant and faint populations. Small changes in the assumed shape of this function can lead to large differences in the estimated total number of galaxies, especially when extrapolating to the faintest end of the spectrum. Redshift effects add another layer of complexity. As light travels through expanding space, it becomes stretched and dimmed, making distant galaxies harder to detect. Correcting for this effect requires precise knowledge of both galaxy evolution and cosmological expansion history. Any small uncertainty in these corrections can propagate into larger uncertainties in final galaxy counts. Dark matter distribution also influences uncertainty. Since galaxies form within dark matter, Halo's understanding the behavior of dark matter is essential for predicting galaxy abundance. However, dark matter itself cannot be observed directly, and its properties are inferred from gravitational effects. While simulations provide strong constraints, they still depend on assumptions about how matter behaves on small scales. Another important factor is galaxy evolution over time. Galaxies do not remain static objects but grow, merge, and change brightness. This means that observations at different distances correspond to different evolutionary stages. Correcting for these changes requires models of star formation, gas dynamics, and feedback processes, all of which introduce additional uncertainty. Instrumental limitations also contribute to variability in estimates. Different telescopes have different sensitivities, wavelength ranges, and observational strategies. Combining data from multiple instruments requires calibration and normalization, which can introduce small, systematic differences. These differences must be carefully accounted for to avoid skewing final results. Gravitational lensing helps reduce some uncertainties by revealing galaxies that would otherwise remain undetected. However, lensing itself introduces complexity, as it depends on the precise distribution of mass between observer and distant sources. Modeling these lensing effects requires detailed knowledge of intervening structures, which are not always fully known. Despite these challenges, multiple independent methods consistently converge on similar ranges for galaxy abundance. This convergence suggests that although uncertainties exist, they are constrained within a relatively narrow band. The agreement between deep-field surveys, infrared observations, simulations, and statistical extrapolations increases confidence in the overall framework. The remaining uncertainty is therefore not about whether galaxies are extremely numerous, but about the precise total number within a given range. Estimates typically vary by factors of a few, rather than orders of magnitude. This reflects the robustness of the underlying cosmological model, even in the presence of observational limitations. Advances in telescope technology continue to reduce uncertainty over time. Improved sensitivity allows detection of fainter galaxies, while better resolution helps distinguish between overlapping sources. Wider surveys reduce cosmic variance by sampling larger portions of the sky. Each improvement narrows the range of possible total galaxy counts. Simulations of cosmic structure also become more refined as computational power increases. These simulations incorporate increasingly detailed physics, including star formation, feedback processes, and dark matter interactions. As a result, they provide more accurate predictions of galaxy populations that can be compared with observations. Despite these improvements, a fundamental limit remains. The universe is only partially observable, and regions beyond the cosmic horizon cannot be measured directly. This means that all galaxy counts are inherently limited to the observable universe. Any extrapolation beyond this boundary remains theoretical and cannot be verified through observation. Uncertainty in cosmic counts therefore reflects both practical limitations and fundamental cosmological boundaries. It arises from incomplete data, complex physical processes, and the finite nature of the observable universe itself. These uncertainties are not signs of failure, but are intrinsic to the nature of studying a vast and evolving cosmos. In the broader scientific picture, these uncertainties define the range within which galaxy abundance is understood. They allow for refinement and improvement, while maintaining consistency with observed data. Over time, as measurements become more precise and models more accurate, the range of uncertainty gradually narrows, leading to a clearer understanding of how many galaxies exist within the observable universe. The large-scale cosmic perspective brings together the full structure of the universe as a single connected system where galaxies are not isolated objects, but parts of an evolving cosmic network shaped by gravity expansion and time. Across the observable universe, galaxies appear in vast numbers, distributed along filaments clustered in dense regions and separated by immense voids. This arrangement reflects the long history of structure formation, beginning with tiny primordial fluctuations and developing into the complex cosmic web seen today. On the largest scales, the universe appears statistically uniform. This means that when viewed across distances far greater than individual clusters or filaments, the distribution of matter becomes smooth and consistent. This uniformity does not erase structure, but places it within a broader balance. Galaxies and clusters form local concentrations, yet no region dominates the universe as a whole when averaged over sufficiently large volumes. Within this framework, galaxy abundance becomes a measure of both structure and scale. The large number of galaxies observed in the universe reflects the efficiency of gravitational collapse acting on initial density fluctuations. Over billions of years, matter has repeatedly gathered into halos-formed stars and assembled into galaxies. Each galaxy represents a local outcome of these universal physical processes operating under the same fundamental laws. Dark matter remains the underlying foundation of this structure. Its gravitational influence shapes where galaxies form and how they evolve, even though it cannot be seen directly. Ordinary matter follows the pattern set by dark matter, filling in the structure with stars, gas, and dust. This relationship creates a layered universe where visible matter traces invisible frameworks. The expansion of the universe continues to influence this large-scale structure. As space expands, distant regions move farther apart, and some galaxies gradually become less observable over time. Despite this expansion, The internal structure of galaxies and clusters remains bound by gravity. This creates a dual behavior in the universe where local systems remain stable, while large-scale separations increase continuously. The question of how many galaxies exist, therefore, becomes not only a numerical estimate, but also a reflection of observational limits and cosmic structure. Within the observable universe, estimates converge on extremely large numbers, representing the cumulative result of billions of years of formation and evolution. These galaxies span a wide range of sizes, masses, and evolutionary stages, yet they all arise from the same underlying processes. Beyond the observable boundary, the situation remains unknown. The same physical laws are assumed to operate, suggesting that similar structures may exist in regions that cannot be seen or measured. However, without direct observation, these regions remain part of theoretical cosmology rather than empirical astronomy. This distinction defines the boundary between measured reality and inferred extension. The universe's large-scale structure also reflects the balance between randomness and order. Initial quantum fluctuations introduced randomness into early density distributions, while gravity amplified these variations into structured patterns. The result is a cosmos that appears both ordered in its large-scale arrangement and diverse in its local details. Galaxy formation continues to be an ongoing process. Even in the present epoch, new stars are forming, galaxies are merging, and structures are slowly evolving. Although the rate of change is slow on human timescales, over cosmic timescales, the universe remains dynamic. This ongoing evolution means that the number of observable galaxies is not fixed in an absolute sense, but changes subtly as the universe expands and evolves. The study of galaxy abundance therefore connects deeply with the history of the universe itself. It reflects the transition from a nearly uniform early state to a highly structured present state. It also illustrates how simple physical laws can produce enormous complexity over time. From tiny initial fluctuations to vast cosmic networks, the universe develops structure through continuous interaction between matter, gravity, and expansion. In the end, the question of how many galaxies exist within the observable universe resolves into an estimate grounded in observation, supported by theory, and shaped by the limits of measurement. It represents not a final fixed number, but a scientific understanding that evolves with improved data and refined models. This understanding continues to deepen as observational techniques advance and as new regions of the cosmos become visible. The universe remains vast, structured, and only partially observable. Within its observable portion lie an immense number of galaxies, each contributing to the overall cosmic pattern. Together they form a coherent picture of a universe shaped by consistent physical principles, unfolding over billions of years and still continuing to evolve in quiet and gradual motion.